Thank you so much for the invitation and the introduction. We are very happy to give this joint seminar here. Naomi and I have been working on various interesting projects in recent times, so it's a particularly great opportunity to be given to do this together. The title of this talk is going to be Modular Space Reconstruction and Weak Gravity, and it's based on a recent paper that we wrote with Ben Heidenreich, Liam McAllister, and Tom Redilis. And the subject of this the talk and the paper is the weak gravity conjecture and geometry. So I hope and I think that many of you will find our results interesting and useful. Let's go.
Yeah, and I just want to echo Jakob's thanks for inviting us to speak here. And I'll just give you an, oops, does this work? I'll just give you an upshot of where we're going in this talk. So what we'll do is we'll verify actually the lattice weak gravity conjecture in a large ensemble of M-theory compactifications on Calabi-Yau threefolds. And in doing this verification, we'll actually be forced to learn how to compute the full Kähler moduli spaces of Calabi-Yau threefolds using a particular kind of BPS index known as Gopa-Kumar-Vafa invariance as the input for that computation. I will not need to say a lot about the weak gravity conjecture to this audience. However, just to set notation, let me say a few words about the weak gravity conjecture, especially in the presence of multiple U1 gauge fields. Well, we'll consider a gravitational theory that contains any number n of U1 gauge fields. And in this setup, the weak gravity conjecture, or more precisely, the lattice weak gravity conjecture version, states that for each, or demands that for each charge, for each site in the charge lattice, which is n-dimensional, there must exist a one-particle state of some mass m, such that its charge-to-mass ratio, as measured by the gauge kinetic matrix, is greater or equal to the charge-to-mass ratio of an extremal black hole in that theory. And our goal will be to test this statement in the landscape of Calabi-Yau threefold compactifications of M theory. So this is 5D n equals to 1 supergravity theories that arise in M theory. Now, conceptually, it's relatively straightforward what there is to do. We have to compute the spectrum of one particle states that are charged under the U1 gauge group. And in this setup, these arise from quantizing the zero modes on M2 branes wrapped on 2 cycles in our Calabi-Yau threefold. Wait, Jakob, isn't that too hard to actually do in practice, to compute the entire one particle spectrum of M2 branes wrapped on 2 cycles?
That's
maybe true. So yeah, I think this is too hard. Maybe something more realistic that we could do is to compute just the BPS one particle spectrum in these theories.
That's good, but that's still very hard. At least I don't know how to do that. It also depends on points in complex structure media space.
Okay, that's a good point. So maybe instead of computing the actual BPS one particle spectrum, we'll compute BPS indices to get a handle on the spectrum. So BPS particles in this setting come from M2 branes wrapped on holomorphic curves. And so the relevant BPS indices are Gopa-Kumar-Vafa, or GV invariants. And these up to higher spin corrections are given as this number here, n sub q0. The 0 just means that this is the genus 0 Gopa-Kumar-Vafa invariant, and the vector q here is a charge that lives in the charge lattice, which is h1 one-dimensional, and it's given by a number of hypermultiplets minus the number of vector multiplets. And GV invariants can be efficiently computed using mirror symmetry. An algorithm was proposed originally by Hassono, Clem, Thiessen, and Yau, but more recently there have been advancements in computing GV invariants and on the computational side. And for the purposes of this talk, we'll take the GV invariants as a black box input into our computation. We won't worry so much about how they're computed, but we'll use the results of that computation.
Naomi, can I ask a quick question?
Yeah.
What is the higher spin stuff that you have there? You have n0q's hypers minus vectors plus higher spin.
Yeah, so there are contributions to the genus 0 GV invariants from all spins.
Okay.
Yeah, is there more to the question?
No, that's it. Thanks.
All right, so finding a non-zero GV invariant for each charge Q in the BPS cone would confirm the lattice weak gravity conjecture within the BPS cone.
That's true, and I agree with everything you said. However, checking a statement this strong will I think not be a useful way to go forward. And to illustrate this, let us look at a particular example of a Kähler threefold hypersurface in a toric variety. So this example is pulled from the Kreutzer-Skarke database. It has H1 equal to 2, so it has a two-dimensional charge lattice, and the BPS cone of Mori cone is likewise a two-dimensional cone, which we can choose to be the first quadrant. And here I'm depicting the genus 0 GV invariants over each integer site in the charge lattice, and so I'm writing the GV invariant over each of these sites. And what you can see in this example here is that while there are many infinite towers populated by GV invariants, there are also infinite number of sites that have vanishing GV invariants. For instance, in this example, you can see the vertical axis comes with a GV invariant equal to 20 at the first site, but then all the following sites will have GV equal to 0. And in fact, in this, one can show that there are no BPS states whatsoever at higher multiples of this site. So now that example illustrates that we can be testing a statement that strong, and in fact, the weak gravity conjecture is not violated in the setup here. And the reason is that for general charges in the charge lattice, the weak gravity conjecture by itself does not actually constrain the BPS spectrum. It just demands that there exist super external particles, but these may or may not be BPS. And so to do something useful with the BPS spectrum alone, we have to restrict our attention to more special charges. Namely, for all charges such that spherically symmetric BPS black holes exist that have charge proportional to that reference charge Q, the particles that are predicted by the weak gravity conjecture, the super external particles, must in fact be BPS. And this you can see as follows. Let us start with the statement of the weak gravity conjecture as I quoted as was quoted on the first slide, which is that the charge to mass ratio of some particle must be bigger or equal than the charge to mass ratio of an extremal black hole. Now, if there exists spherically symmetric BPS black holes, then the mass of that black hole is computed by the central charge. So we can replace that by this expression. And the mass of any particle in the theory at that charge is constrained by the BPS bound, which takes the same form as the weak gravity bound, except that the inequality goes, there we go, goes in the other direction. So we see that the charge to mass ratio appears on both sides, and thus all inequalities must be saturated, and the particles satisfying the weak gravity conjecture for such special sites in the charge lattice must in fact be BPS. So what does the weak gravity conjecture predict in terms of the BPS spectrum? The lattice weak gravity conjecture predicts infinite towers of BPS particles within the cone of spherically symmetric BPS black holes, which we will refer to as CBH. And so it is within this cone, that we will test the predictions of the weak gravity conjecture. Here's a picture of, why is this not moving? Oh, here we go. Here's a picture of how the cone might look like. There's a cone of spherically symmetric black holes, which lives inside the Mori cone, but it's not equal to the Mori cone in general. And so our first task will be to compute this cone, i.e. the cone in charge space where extremal BPS where spherically symmetric BPS black holes exist.
Huh. Okay, well, I think I have an idea on how to actually go about computing that. We know that BPS black holes exhibit the attractor mechanism. And so that means that massless scalars flow to the same values, specific values on the horizon of the black hole, regardless of the values that those scalars take at spatial infinity. So we can use the fact that these BPS black holes exhibit the attractor mechanism as a diagnostic to detect BPS black holes. So again, we want to compute this cone CBH to the best of our ability. And there's a correspondence because of the attractor mechanism between the charges of spherically symmetric BPS black holes and moduli vevs on the horizons of those black holes. And to be specific, these moduli vevs can take values inside what's called the extended Kähler cone. So if we have a particular Calabi-Yau X, we construct the extended Kähler cone by taking the union of all the Kähler cones of all the Calabi-Yaus that are birationally equivalent to X. That's the extended Kähler cone, and that's where these moduli vevs can take values. And so the cone of BPS black holes contains the moduli space itself. That's what the attractor mechanism tells us. And it contains the moduli space expressed in a certain set of flat coordinates. So it turns out that this cone of BPS black holes contains a cone T, which will be our one of our main objects of focus. And T is the set of all values tau equal to 1/2 J wedge J, where J is the Kähler form of the Calabi-Yau. So this is a cone that is computed piecewise over all of the different chambers of the extended Kähler cone. And in particular, a nice fact about this cone T is that these coordinates sweep out the dual of the cone of effective divisors or effective holomorphic force cycles of the Calabi-Yau. So in particular, we have the relation that our cone T is equal to E dual, where E is the cone of effective divisors. The upshot of this slide is that in order to compute the region in charge space where BPS black holes can exist, we need to compute the moduli space. And moduli space is the extended Kähler cone. So we really need to compute the extended Kähler cone.
And that's great news, I believe, because there's a lot we can say, I think, about the extended Kähler cone from using toric geometry. And in order to make this explicit, let us consider as a testing ground the largest known database of Calabi-Yaus, which the famous Kreutzer-Skorke database, which is based on hypersurface. The Calabi-Yaus in this data set can be viewed as hypersurfaces within toric varieties whose toric fans are induced by fine, regular, and star triangulations of reflexive polytopes in 4 dimensions. And in this setup, we can say a lot about the extended Kähler cone. And again, okay. Sorry if this is a little stuck. A reasonable approach to this is to find all suitable triangulations, i.e. fine, regular, and star triangulations of a given reflexive polytope delta. And for each phase, construct the corresponding Calabi-Yau hypersurface and compute the torically induced Kähler cones for each of these phases. One can then patch them together. Different triangulations give rise to birationally equivalent Calabi-Yaus, and one obtains sometimes a very complicated phase diagram of Calabi-Yau compactifications. Here's a 2-dimensional cross-section through the FRST, if you want, extended Kähler cone depicted for the reflexive polytope with the largest value of H11 equal to 491. And this figure was made by Andres Rios-Tascon. And you can see here that there are very many phases, and we can patch them together just using toric geometry.
Wait, but Jakob, sorry. The FRST extended Kähler cone, that's not the entirety of the extended Kähler cone, right? So in general, the actual extended Kähler cone of a particular geometry is going to be bigger than just the piece of it that you get from FRSTs of a particular polytope. For example, in this phase diagram of 491 that you showed on the previous slide, there could be many more what we'll call non-toric phases beyond just that FRST extended Kähler cone. So these are geometries, they're Calabi-Yaus that are birationally equivalent to any of the Calabi-Yaus on the inner part of the diagram. But they can't manifestly be written as toric hypersurfaces, or they're not given by FRSTs of the same polytope or perhaps of any polytope. But this is okay. Let's actually use this fact as an excuse to really investigate how to go beyond the toric lamppost and find all of moduli space. And we should also take this as some kind of warning that whenever we do landscape searches within compactifications on Calabi-Yau's that come from the Kreuzer-Skarka database, there might be lots more non-toric phases that we're neglecting. So let's figure out how to go beyond just these toric hypersurface Calabi-Yau's.
That is great. I subscribe to that, and let us make the following our main point. Let us start only with the GV invariance, the genus-toric GV invariance of a given Calabi-Yau X, and let us construct the entirety of the extended Kähler cone using that information. So going, in particular, going beyond the part of modular space described by toric geometry. Now, the rough idea is, of course, that the GV invariance will tell us which curves can shrink without inducing an infinite number of massive states at finite distance. And in order to use this to actually construct modular space, I'll describe first abstractly how this can work, and then we will apply this technology to the example that we showed earlier. And first of all, a reminder: the extended Kähler cone is the union of all Kähler cones of all birationally equivalent geometric phases. And you can think about these phases of these cones as being glued together along facets. So we need to understand the physics. So in order to compute this cone, we need to, and in particular infer where the phase transition loci lie from just the BPS invariance. We need to understand the realm of possible physics along facets of Kähler cones. And happily, this has been classified by Witten, and there are essentially four options. The first option is that of a flop, where any number of isolated rational curves shrinks to a point, for instance, a conifold, and a finite number of states become massless, in this case, hypermultiplets. The second option is a little bit more complicated and corresponds to loci of non-abelian SU2 enhancement from U1 to SU2, where also a finite number of low spin states become massless. In this case, we can have hypermultiplets and vector multiplets, and this corresponds to rational curves shrinking that have a one-dimensional complex one-dimensional moduli space. Then there are two further options that will not show. Okay. The third option is that of a strong coupling limit. So this corresponds to a divisor shrinking to a point. And in this case, this can happen at finite distance in modular space, but an infinite number of electric states become massless, as well as a tensionless string. The fourth option lies at infinite distance and corresponds to an infinite number of electrically charged states becoming massless at weak coupling.
Okay, one question though, from what you've said so far, it seems like numbers 1 and 2, those options, might look very similar or actually the same from the point of view of the GV invariance, because they both involve finite numbers of states becoming massless. Do you think that just for the time being, we could ignore this second option that seems a little bit more subtle about the SU2 enhancements? And let's look at the physics that can happen when we ignore that possibility, and then at the end, maybe we can come back to that and see how our story changes if we start including SU2 enhancements.
That sounds great.
Great. So let's ignore that for now. Let's assume that this option doesn't happen. And then let's try to classify these the GV invariance in terms of these different possibilities of the physics. So a flop transition, if we go back to our example with H11 equals 2, here's the GV invariance of that example. A flop transition corresponds to shrinking a generator of the Mori cone that looks like this. So this is a generator array that has a finite number of a non-zero GV invariance and then an infinite number of zero GV invariance. In contrast, one of these strong coupling or infinite distance limits would correspond to shrinking a generator of the Mori cone that looks like this one, i.e. has an infinite number of non-zero GV invariance along it. And actually, as it turns out for this particular example, shrinking this generator happens to be a strong coupling limit. But both of those limits would look like this. And so our overall goal is to actually identify flops from the patterns in GV invariants like this one. And so to make this a little bit more precise, let's make a few definitions that we'll use this example to make. So a nilpotent curve is a ray like this one. It's a ray with finitely many non-zero GV invariants. In contrast, a potent curve is a ray with infinitely many non-zero GV invariants, and any ray inside of this blue cone is a potent curve because it has an infinite number, presumably, of non-zero GV invariants. And finally, we'll define something called a NOP curve, which stands for nilpotent outside of potent. And this is a curve, again, like this red one in the picture. It's a nilpotent curve outside of the closure of the cone generated by potent curves. So in this picture, you can see that the potent curves form this blue cone, and this red ray is strictly outside of that cone. So this is what we would call a NOP curve. And so what we really want to do is use these GV invariants to understand the entirety of the moduli space through flop transitions.
That's great. And in order to do this, I think we can proceed as follows. Let us use as a computational tool the four-dimensional theory that arises from compactifying the five-dimensional theory we started with on a circle. So this is type 2A string theory compactified on the same Kähler. And in this case, the prepotential that governs the complex structure module, the vector multiplet sector is a holomorphic function of the moduli. And it can be written as follows. It has a binomial piece denoted P in this equation, whose leading cubic term is computed by the classical triple intersection form. And it also receives an infinite tower of worldsheet instanton corrections. So this comes from worldsheet instantons wrapping effective curves. And they're not surprisingly, their amplitudes are given by the genus zero GV invariant of any given curve class C. Now we want to use this expression to analytically continue past a facet in Kähler moduli space where a knob curve shrinks. So let C0 be such a knob curve. And under our assumptions that we are currently working with, this will be a flop curve, but we will be general in this discussion. And now we vary the Kähler parameters such that the volume of this curve, as measured by the Kähler form, formally becomes negative. And by doing this, we will enter the new Kähler cone, the Kähler cone of a new Calabi-Yau threefold X prime, which will then be birationally equivalent to X. And we want to use the holomorphic prepotential to compute the geometric data of this new threefold X prime. And how do we do this? Well, first of all, let's write out the very same prepotential I wrote down on the previous slide. But let's isolate the contribution to it to the prepotential from curves from worldsheet instantons wrapped on our knob curve C0, here marked in red, and separated from all other contributions. Now we assume that we've gone into a realm of moduli space where the volume of our curve C0 has become formally negative. And so it makes sense to redefine a new curve class C0 prime, which is minus C0, such that its volume is formally positive. And now we can write down the same prepotential again. Nothing has changed. I've just substituted the definition I've made. So now everything is written in terms of volumes of positive volumes of curves. However, the contribution from the curve C0 prime cannot be as such interpreted as an instanton correction because the sign is off in the exponent. However, we can use a very old identity of the polylogarithm due to Gendler, which relates the trilogarithm of e to the minus x to the trilogarithm of e to the plus x, plus an additive polynomial piece that's in fact cubic in the argument of the exponential. And of course, once we do this, we can absorb this cubic term into the polynomial piece of the prepotential, and we can write this in the same form as we did previously, but with corrected triple intersection numbers, and as it turns out, also corrected second term class. And this is how we compute the classical geometric data of the flopped face.
Okay, so that was a little abstract. Let's step back and ask what we've actually learned. So we've learned that an isolated generator of the Mori cone with a finite number of non-vanishing GV invariants, i.e. a knot curve, can be flopped in order to obtain a new Calabi-Yau. And so by performing all available flops to uncover all Calabi-Yaus, i.e. finding all of those knot curves given a set of GV invariants, we can determine the entirety of the extended Kähler cone. So that's the general idea. And now let's see this in our concrete example from earlier. So let's again consider this same set of GV invariants that I showed you earlier for this Calabi-Yau threefold with H11 equals 2. And again, in this example, the entirety of the first quadrant is the Mori cone of the Calabi-Yau X. And we saw earlier, so just for visual clarity, let's actually replace every non-zero number here. So everywhere we see a number that's non-zero, let's just replace it with a dot. And we saw earlier that there was this curve here on the y-axis that we could actually identify as a knot curve. And in fact, this curve can actually be flopped. So by taking this curve C0 to minus itself, we're supposed to get a new Calabi-Yau X prime, which is birationally equivalent to the Calabi-Yau X that we started with. So let's actually just do that. Let's take this curve C0 and flop it to minus itself. And as promised, we end up with the Mori cone, which is this pink shaded region of our new Calabi-Yau X prime. And as a fun fact about this example that we picked, and this is actually why we picked this example, this new Calabi-Yau X prime that you get from flopping this curve C0 turns out to not be in the Kreuzer-Skarka database or in the CC database. So to the best of our knowledge, this is really a new Calabi-Yau in some sense. All right, so we have this picture of the Mori cone of X, which is the first quadrant in blue, and the Mori cone of X prime, which is this pink cone. And what does this look like on the Kähler side? So how do we actually get the extended Kähler cone from this? Well, we simply take normal cone duals. So if we take the cone dual of the Mori cone of X, we obtain the Kähler cone of X, which is again just this blue quadrant. And if we take the cone dual of the Mori cone of X prime, we get the Kähler cone of X prime, which is this narrow pink cone on the Kähler side. And so we've achieved our goal. The union of these two Kähler cones is the extended Kähler cone of this geometry. So we've gone from the GV invariance to the extended Kähler cone as promised. And now, remember, this talk is about checking the weak gravity conjecture. So let's take it one step further and actually check the weak gravity conjecture in this example. So here's our extended Kähler cone. It's the union of the Kähler cone of X and the Kähler cone of X prime. And now we can just apply the dual coordinate map that we introduced earlier. So this just takes the Kähler form J to 1/2 J wedge J. And what do we end up with? Well, on the Mori side, we end up with a cone T, shown here in yellow, which is strictly contained inside the intersection of the Mori cones of X and X prime. All right, so this is good news. Why? Why is it good news? Well, every site in this purple region, the intersection, hosts a BPS state. And our cone T is contained in the purple region. And so the lattice weak gravity conjecture is satisfied because every site inside of this yellow cone is populated with a non-zero GV invariant. Cool. So it seems like we're in a good position to check the weak gravity conjecture in lots of examples.
But wait, not too fast. I believe everything you said is true, and in this particular example that you showed, I see no problem. However, let's remember that we made an important simplifying assumption in the beginning, namely that there are no loci of SU2 enhancement anywhere in moduli space. And perhaps it's now time to revisit this. So the reason why we had made this simplifying assumption is that at the level of the GV invariance, the curves that shrink to produce, or the BPS invariance of curves that shrink to produce these singular loci in moduli space look very similar to those of flops. So let's revisit what happens when these loci exist. And in particular, we have to address how the previous discussion that we made changes in the presence of such non-abelian loci in moduli space. And a key point is that along some facets, but not all of them, that correspond to SU2 enhancements, the curves that shrink to produce the massive states that realize the non-abelian theory turn out to come from shrinking a knob curve as well. So at the level of GV invariance, we cannot distinguish such loci from flop loci. And so for this reason, we will refer to such to transitioning through such facets of the Kähler cone as a Weyl flop. And if we now naively apply the previous discussion for the previous procedure for computing the pre-potential, we can still apply it. We can analytically continue the pre-potential across such a facet of the Kähler cone, and we'll end up with something that looks like a new phase. We'll compute new triple intersection numbers, new second trunk class, and this very much looks like a new Calabi-Yau. But this is not actually true. So really, let us see what does it mean physically to go through a Weyl flop. First of all, the new phases turn out to actually not be part of the extended Kähler cone because holomorphic force cycles shrink along the facets that correspond to the non-abelian enhancement. And this is as it must be because M5 branes wrapped on such shrinking force cycles realize the top Polyakov monopole string. Now, instead of producing a genuinely new phase, what happens is that it produces chambers in modular space that are related to the original phase by the Weyl group of SU2. And this is a gauge symmetry. So the phase that lies, the part of modular space that lies behind facets of the Kähler cone of this form turns out to be gauge equivalent to regions of modular space that we started with. So in practice, we see that this is actually relatively harmless because all this means is that if we overextend the Kähler cone by passing through such facets as well, we will construct a universal cover of modular space. Oh, sorry. Oh. And now in going through the previous discussion and filling out and computing is in particular the cone of spherically symmetric black holes, one can show that provided that such a locus appears from shrinking a knob curve, the additional sites in the Mori cone that one computes with this procedure will still host BPS black holes, spherically symmetric BPS black holes. And this is as it must be because and these are related. These are inequivalent to the ones we started with, but they are related to the original ones because they live in the same SU2 multiplet.
Okay, cool. So I think now we've covered all the physics that can possibly happen as we go through facets of the Kähler cones. So I think we're really ready to check the weak gravity conjecture in a large ensemble. So for a given Calabi-Yau, we now have an algorithm to verify the weak gravity conjecture. First, we compute the Gopa-Kumar-Vafa invariance up to some finite degree. From that set, we determine the extended Kähler cone by going through all possible flops, and in fact, by going through all possible Weyl flops as well. Then we apply the dual coordinate map to that extended Kähler cone in order to obtain our region T in the cone of BPS black holes. And then we ask, is every site in T populated by a non-vanishing GV invariant? If so, then the weak gravity conjecture, and in fact, the lattice weak gravity conjecture is satisfied in that example. So this is exactly what we did in over 2,000 Calabi-Yaus constructed as hypersurfaces in toric varieties. And in fact, not just in those Calabi-Yaus, in all flopped phases of those Calabi-Yaus as well. So you can think of this as roughly 2,000 seed Calabi-Yaus. And what we found is that in every single geometry, the lattice weak gravity conjecture was always satisfied. So that's what we found as pertains to the weak gravity conjecture, but you may also be wondering about these non-toric phases that we alluded to in the beginning of this discussion. How many of these new non-toric phases did we in general find? So here are some results on that. So in each of these pictures, the x-axis is just some arbitrary identification of the polytope. And on the y-axis is the number of toric or non-toric phases that we found in that geometry. or for that polytope. So in blue is the number of toric phases, and in orange is the number of non-toric phases. And you can see that even at H11 equals 2, there start to be some non-toric phases. And in particular, the example that we kept showing you throughout this talk is this first orange bar here. So that's a Calabi-Yau that we couldn't find in the KS database or in the CC database. And what's interesting is that as we start to go up in H11, we see that the number of non-toric phases starts to grow and grow. And in fact, already at H11 equals 4 and above, these non-toric phases start to dominate over the toric phases. So these are really an important part of the Calabi-Yau landscape. All right, so that concludes sort of our main discussion. And now we want to take the opportunity to sort of spin this story in a way that we think is kind of cool. And this is an instance, which I think is one of the coolest instances of using the weak gravity conjecture. It's a case where the weak gravity conjecture actually informs geometry. So what we saw is that the cone of BPS black holes is related to the effective cone of divisors. And what we have done in practice is to compute the effective cone duals in a large ensemble of geometries, and then verify that all the sites in those cones are populated with non-zero GV invariance so that the weak gravity conjecture is satisfied. But I wonder, could we possibly turn this logic around and actually go the other way and use the weak gravity conjecture to constrain effective cones?
That's a great idea, and I think you're absolutely right. We can do this. And suppose, for example, that we're confronted with the following situation. We consider some Calabi-Yau hypersurface, let's say, and we compute an approximation to the effective cone, which is an inner approximation. So E approx sitting inside the true effective cone E. Now we might be confronted with this picture where the dual of this approximation, viewed as a subcone of the Mori cone, contains a lot of sites with non-zero GVs, but also a lot of sites with vanishing GVs. In particular, it can happen, and this is what happens in this toy example here, that there are rational arrays that have a strictly vanishing GV invariance. So in this case, So in this case, there would indeed be empty sites in the dual of the approximate effective cone. And so what the weak gravity conjecture, or the lattice weak gravity conjecture, then predicts for us is that our approximation was not good enough, i.e. that E approx is not actually equal to the effective cone. And the Calabi-Yau in question here should really have more effective divisors. Oh, sorry. Oh, okay. And this is because, okay, I'm going back and forth. This is because the true effective cone, dual of the true effective cone should host infinite towers of BPS particle states throughout. So this is how the true effective cone, the true dual of the effective cone should look like in this example. And this turns out to be very, very, very useful because in the set of toric geometry or the Kreuzes-Skorpio database, it is actually very easy to compute an approximate effective cone, and this goes as follows. When the toric fourfold that we start with has toric divisors, we can intersect those with the Calabi-Yau hypersurface to obtain effective divisors in the Calabi-Yau. And so every divisor we find in this way is in fact effective, but not all the divisors in the effective cone might be able to be written this way. So this is something that happens in the Kreuzes-Skorpio database when we scan through it. And so we can use this as a workable diagnostic for non-inherited effective divisors. Let me conclude. We have done two things. We have used the genus zero Gopa-Weyl invariance to reconstruct the Kähler modular space of Calabi-Yau threefolds in its entirety, essentially. So in particular, we've gone past the part of it that is governed by toric geometry. And equipped with this technology, i.e. the full Kähler modular spaces, as well as the collection of BPS states computed from the BPS index, we verified that the weak gravity conjecture and actually the lattice weak gravity conjecture holds in a plethora of examples. And
Okay, great. So we will just leave you with some food for thought that hopefully can facilitate some fun discussions. Some things that were sort of surprising to us or not clear how it works. So first of all of the examples that we checked, as you saw, appeared to satisfy the weak gravity conjecture with genus 0 GV invariance. That alone is not so surprising because we saw that higher spin particles contributed to the genus 0 GV invariance, but it didn't have to happen that way. Also, as we saw, all of the examples that we checked actually satisfied this strong lattice version of the weak gravity conjecture that in fact has counterexamples in general. So why did that happen to be true? Something we didn't touch on, but we spent a lot of time computing this cone T and looking for infinite towers of BPS indices inside that cone T, but there's also often infinite towers of BPS particles outside of that cone. And so question, do those infinite towers play any role in either any form of the weak gravity conjecture, or are they necessary for any other sort of physics? And perhaps relatedly, we can ask a question about non-spherically symmetric BPS black holes. So in this talk and in this project, we focus specifically on the spherically symmetric kind because that's where we can most easily apply the attractor mechanism, but you could ask similar questions for non-spherically symmetric black holes. And finally, what happens when the attractor flow runs into CFT bounds?
2, 4, 8, 1.
In other words, what is the cone of spherically symmetric black holes in general? And with that, we will say thank you.
Thank you very much.